Hi, this is week 17 of chemistry, and this week we'll be talking about stoichiometry. So for our lesson objectives, students will be able to perform stoichiometry calculations involving mass problems. There are variations, there's mass, but it's also volume to mass, particles to mass, mass to volume, and so on, all sorts of variations, but we'll focus just on mass problems involving stoichiometry. So what exactly is stoichiometry? Stoichiometry is the calculations of reactants and products in a chemical reaction. So if you have a chemical reaction, I give you the products, so you should be able to go ahead and figure out how many reactants you began with, or vice versa. If I give you the reactants, you should be able to calculate how many products you will create. You may also be able to figure out how many reactants you need to react with additional reactants. Stoichiometry is founded on the law of conservation of mass, where it states that whatever amount of molecules you begin with, that's the same amount that you gotta end with. Molecules are merely rearranged in a chemical reaction. So the mass at the beginning, the reactants, should equal the mass at the end, which is the mass of the products. So what are steps for solving a stoichiometry problem? So it says stoichiometry solving by, number one, balancing the reaction. For our problems, our equations will already be balanced, but if they're not, that will be step number one. Step number two, convert the given quantity to moles. Alright, so you're going to get, in this type of mass problems, you're going to get your given in grams, and your first step is change those grams to moles using the molar mass. Number three, use the mole ratio. In the mole ratio, what you're going to go ahead and do is you're going to look at the chemical reaction that has already been balanced, and you're going to go ahead and figure out how many moles am I using, how many moles will be produced for a particular molecule that was given, and the particular molecule that you're looking for. At the end, step 4, we're going to go ahead and get those moles of whatever it is that you're looking for and go ahead and convert them from moles back to grams. So those are our 4 steps. For us, mainly we'll focus on step 2, 3, and 4 because our equations will already be balanced. The section on balancing equations was covered in a previous video. Let's go ahead and move on to our first example. In this problem, they go ahead and they ask you how many grams of CO2, carbon dioxide, are produced by the combustion of 232 grams of C4H10, which is butane. Butane can be used in little stoves. If you're going to go ahead and go on a camping trip, you can go ahead and take it with you in a little container. So there's a chemical reaction for this combustion reaction. So here's our balance equation. And I know that this equation is balanced because I am given the coefficients in the front. So there's 2 molecules of butane reacting with 13 molecules of oxygen, and that will yield 8 molecules of carbon dioxide and 10 molecules of water. Alright, so of all those values though, I'm really only concerned with these guys. The butane, since that's our given, the 2 moles of butane, and the carbon dioxide, that's the one they asked me for. So for the carbon dioxide, notice they didn't ask for how much oxygen was required to react, so I'm not going to be too concerned with the oxygen. Same thing for the water, I'm not too concerned with it. So let's go ahead and solve this problem. So for the balance equation, I'm going to go ahead and write it again. So we're going to have 2 molecules of butane, and that's going to react with 13 molecules of oxygen, and that's going to go ahead and give me 8 molecules of carbon dioxide and 10 molecules of water. Alright, so there's our mole ratios. For every 2 butanes, you need 13 oxygens, and that will yield 8 moles of carbon dioxide and 10 moles of water. So what do we do first? Well, the balance equation, that's already balanced. So let's move on to our next step. Our next step is to go ahead and convert our grams to moles. So our given is 232 grams of butane. So I'm going to go ahead and write it here. I have 232 grams of butane, and my goal is to go ahead and get these grams and convert them to moles. So I'm going to go ahead and do that. So I'm going to put 1 mole on the numerator. In the denominator, it's going to be the molar mass of butane. So I got to go ahead and solve for that. Molar mass of butane, let me go ahead and do it here off to the side. There are 4 carbons and 10 hydrogens. See, there's 4 carbons and 10 hydrogens. Now I get the mass from the periodic table. Carbon is 12. Hydrogen, we'll just put 1.0. We're rounding it off to nearest 10th. Now let's go ahead and multiply. It's going to be a 48. And that's going to be just 10. So it goes a grand total of 58 grams per mole. That's the molar mass of butane. So I'm going to go ahead, and that's the number that goes right here. Notice that's in grams. My given's in grams, so I need to put grams in the denominator so that they can cancel out, and its molar mass is 58. At this point, I'm going to go ahead and get my calculator and put in our given 232, multiply it times 1, and then divided by our molar mass, which was 58. That's going to give us 4 moles of butane. Alright, so that's our very first part. So we went ahead and switched the grams to moles. Alright, next we're going to go ahead and get this right here, our 4 moles of butane, rewrite it here for our second step, which is the mole ratio. So I'm going to get my answer, rewrite it. That's going to be 4 moles of C4H10. And for our mole ratio, again, I looked at the balance equation, and that's our given, so that's why I'm looking at it, and that is what we're looking for. Our question was for carbon dioxide. They did not ask for water, they did not ask for oxygen, they asked for carbon dioxide, so that's why I'm zeroing in on both of these. Alright, so what do I do now? Well, I want to cancel out my given and replace it for the molecule we're looking for, in this case carbon dioxide. So the given, I want to cancel out by putting this 2 moles of butane on the denominator and match it up with 8 moles of carbon dioxide on the numerator. Now notice what happens here. My butane is gone, and now I have carbon dioxide, which is the molecule that we're solving for. So the mole ratio step is to go ahead and switch from one molecule that was given to the molecule that we're looking for. That's its purpose. So what do I do now for my calculations? I multiply 4 times 8 divided by 2. So my answer is 16 moles of carbon dioxide. So I switch from the moles of butane, which is our given, to the moles of carbon dioxide, which is the molecule that we're looking for. Our final step now is, now we have the moles of carbon dioxide, but our question was, can you find how many grams of carbon dioxide? So our last step is to go ahead and switch from moles back to grams. So we're going to go ahead and do that. I'm going to get my answer one more time here, rewrite it here, 16 moles of carbon dioxide, and I'm going to go ahead and convert it from moles back to grams. So I'm going to put moles, I need them to cancel out, so I'm going to put them in the denominator, so that way they can cancel out, and the grams will go on top. Now, how many grams is that? Well, we need the molar mass of carbon dioxide. So, just like I solved for the molar mass of butane, I'm going to go ahead and solve for the molar mass of carbon dioxide. So I'm going to go ahead and, let's see, it's going to be, there's 1 carbon, there's 2 oxygens, mass from the periodic table, carbon is 12, oxygen is 16, again we're rounding off to nearest tenth, and I'm going to go ahead and multiply, that's 32, so my molar mass of carbon dioxide is 44 grams per mole. So that's the number that's going to go here, 44 grams for every mole. Put this into our calculator, it's going to be 16 multiplied times 44 divided by 1, and that will give us our answer in grams, because the moles get cancelled out, so it's going to be in grams, which is what they asked for, how many grams of carbon dioxide. So let's see, it's going to be 16 times 44 divided by 1, so our answer is 704 grams of carbon dioxide. So there you have it, that's our answer. Now I wanted to go ahead and do a quick recap one more time. So first step, we looked at the balance equation. In this problem, we were going from butane to carbon dioxide. So what we did first was to convert our given to moles. So I'm going to write that down. Given to moles. That was our first step, convert our givens to moles. Alright, so that's what I did here. Notice I put the grams in the denominator so that they can cancel each other out. Moles in the numerator. So we ended up with 4 moles. What happens next? What happens next is a mole ratio. And in our mole ratio, we go ahead and we take the moles of the given and change it for moles of the molecule you're looking for. The values here came from the balance equation. And our last step is to convert, one more time, our moles back to grams. Moles to grams. That will be for our mass-to-mass problem. It's a mass-to-mass problem because we started with grams and we finished with grams, both are mass. Alright, so that takes care of example 1. For our next example, example 2, they're going to go ahead and ask us a very similar question. Same butane reaction, But this time they ask you how many grams of oxygen are needed to react with 580 grams of butane. Alright, so it's a same balance equation, but now instead of asking me for the carbon dioxide, they're asking for how much oxygen would you need to react. So they give us the reactant, and they're asking what else you need to react with our 580 grams of butane. Alright, so we're going to go ahead and solve this problem. Again, though the changes, they're not asking us for carbon dioxide, they're asking for how much oxygen will we need to react with our given amount of butane. So let's go ahead and get started. First of all, we get our given, which was 580 grams, and we're going to go ahead and switch it to moles. Alright, so I'm going to go ahead and write 580 grams of butane, C4H10, and I want to switch it to moles, so the grams will go in the denominator, 1 mole in the numerator, so that way the grams will cancel out, and our answer will be moles. First step is you got to switch the given to moles. I need the molar mass of butane. I had sulfur in the previous problem. Here it is. It is 58 grams. So I'm going to go ahead and multiply 580 times 1 divided by 58 grams. And that's going to go ahead and give me 10 moles of butane. Next, I get my answer. I'll rewrite it in the second step, which is a mole ratio. 10 moles of butane. And now, what I'm going to go ahead and do is, I'm going to go ahead and look for how many moles of oxygen gas I needed to react with my butane. So look at the coefficients for a balanced reaction. For every 2 butanes, you need 13 oxygen molecules. Alright, so I'm going to go ahead and put, for every 2 moles of butane, you need 13 moles of oxygen. Alright, so notice that the butane will cancel out, and the molecule we're looking for, who's in the numerator, that's what we're going to get. We're going to left with moles of oxygen. So it's going to be 10 times 13 divided by 2. I believe that gives you 65 moles of oxygen gas that butane canceled out. Alright, so what's next? Our third and final step. We're going to get these moles of oxygen and switch them from moles back to grams. And that will be our answer. So we have 65 moles of oxygen gas. And we're going to put moles in the denominator so that they can cancel each other out. It will be grams in the numerator. Grams of what? Grams of carbon dioxide? No, grams of oxygen, since that's what we're looking for. Alright, so I'm going to go ahead and do the work for that. Oxygen is, there's only O2, which is, there's 2 oxygens. Molar mass is 16.0, so that gives us 32 grams per mole for oxygen. So that's the number I'm going to put here. So it'll be 65 times 32. And that's going to go ahead and give us our answer. So our answer is 2,080 grams of oxygen gas. That's how many grams of oxygen gas you would need to react with 500 grams of butane gas. Let's go ahead and keep on moving to our next example. In example 3, they go ahead and they ask us, how many grams of oxygen gas are needed to react with 100 grams of hydrogen? Hydrogen gas is very flammable. As you can see in this picture right there, in this movie they filled up hydrogen gas and ignited, and you get a pretty nice explosion. So for hydrogen, it's reacting with oxygen and it's producing water. But the question here is, you have 100 grams of water, of hydrogen, how many grams of oxygen do you need to react with it? Alright, so I'm going to go ahead and erase the previous problem, write the balance equation for this new problem. So for every 2 moles of hydrogen, you need 1 mole of oxygen. And that's going to yield 2 moles of water in a chemical reaction. So that's a 2. Usually a 1 is not placed, so but I did so that you know where I'm getting the value for it. So if it's usually blank, that means that there's a 1 right here. Alright, let me erase the previous work and start solving this one. Alright, so what are we going to do with our given? Switch it to moles, right? So our given is 100 grams of hydrogen. Let's go ahead and write it down. You have 100 grams of hydrogen gas. I'm going to put 1 mole in the numerator. The denominator is going to be the grams. Molar mass of hydrogen is just 2. Alright, so you're going to end up with 50 moles of hydrogen. Molar mass of hydrogen is 2. I'll show the work for that one. Hydrogen, there's 2 hydrogen atoms, and on the periodic table, molar mass of hydrogen is 1.0, so that's how we got our 2.0 grams per mole. So that's our molar mass for hydrogen. Now that I got my 50 moles of hydrogen, I'm going to go ahead and use the mole ratio now. I'm going to go ahead and rewrite it here. So I get 50 moles of hydrogen gas, mole ratio. That's when I look at the balance equation. For every 2 moles of hydrogen, you need 1 mole of oxygen. It's just a 2-to-1 ratio. Who goes in the numerator, who goes in the denominator? Well, I want to cancel out the hydrogen, so I better put the hydrogen on the denominator so that they can cancel out. And there's 2 moles of hydrogen for every 1 mole of oxygen. So my calculator will put 50 multiplied times 1, then divided by 2, and that's going to go ahead and give us our answer, which is 25 moles of oxygen. The hydrogen canceled out, that's why it's oxygen. Final step, get those moles, switch them to grams. So I got 25 moles of oxygen. And I'm going to put moles in the denominator so that they can cancel out. And the grams on the top, the molar mass of oxygen. Oxygen gas is O2, so there's 2 oxygens. Molar mass is 16. So that's going to give us 32 grams per mole. That's the molar mass of oxygen, 32. So I'm going to go ahead and put that right there. So it's going to go ahead and be 25 times 32 divided by 1. That gives us a value of 800 grams of oxygen gas. That's our answer. So for every 100 grams of hydrogen, you're going to need 800 grams of oxygen so that they can react with each other to produce water. That takes care of example 3. Let's go ahead and move along to our next problem, which is number 4. In number 4, they ask you, how many grams of water are produced by the reaction of 200 grams of hydrogen gas? Alright, so it's a very similar problem again, and we have water reacting, but this time they're asking for the product. Previously they had asked for the reactant, how much oxygen we need to react. In this case, they're asking for how much water will be produced. Alright, so now I'm going to go ahead and erase the previous problem. And now we're looking for this one. They're giving us hydrogen and they want how much water will be produced. Alright, so we're going to get our given, which is 200 grams of hydrogen. And again, first step, take your given, convert it to moles. So I'm going to put 1 mole on the top, on the bottom. Molar mass of hydrogen was 2 grams. So that's going to give me 100 moles of hydrogen. Alright, get that, rewrite it here. Next step, let's look at our mole ratio. For every 2 moles of hydrogen, you get 2 moles of water. So I'm going to write these here, 2 moles of hydrogen, I get 2 moles of water. Alright, notice that the hydrogen cancels out, so it's going to be 100 times 2 divided by 2, we still get the same 100 moles of water. So notice, what's the point of that second step if we get the same value? Well, it was to replace the hydrogen, which is our given, for what we're looking for, which in this case is water. Alright, now that we have this, we're going to get this answer and I'm going to switch it from moles back to grams, and that will be our answer. So we have 100 moles of water, and I'm going to put the moles in the denominator so that way they can cancel each other out. Grams in the numerator. Molar mass of water is 18, so our answer will be 1800 grams of water. Alright, the work for the molar mass, to solve for the molar mass of water, how do we get that 18? Well, we'll go ahead and count how many hydrogen atoms, how many oxygens in water, 2 hydrogens, 1 oxygen. Molar mass of hydrogen is just 1. Molar mass of oxygen is 16, so 1 times 16, 16. So our grand total is 18 grams per mole, and that's where this 18 came from. And after that, multiply, divide by 1, you get your answer. 1800 grams of water are produced by the reaction of 200 grams of hydrogen gas. That takes care of example 4. Up next, example 5. In example 5, we're looking at the creation of ammonia, where you have 1 nitrogen reacts with 3 hydrogen, and that will go ahead and give you ammonia, which is used in household cleaners. Alright, so how many grams of nitrogen are needed to react with 30 grams of hydrogen? Again, they are asking about the reactants here. So they could ask you for both reactants or a reactant and a product, or if there happen to be 2 products, they can ask you to solve for both of those. Any combination of any one of the molecules reacting. So let's go ahead and get to work on it. Alright, and I'm going to put 1 nitrogen right there. Again, if there's no number, it means that there's a 1. Plus 3 hydrogens, and that's going to go ahead and yield 2 NH3 molecules, which is called ammonia. Alright, ammonia is used as a household cleaner, also fertilizers among other products as well. So let's go ahead and get started. Our given is 30 grams of hydrogen. There it is, 30 grams of hydrogen. So I'm going to go ahead and write that down. I have 30 grams of hydrogen gas. That's our given right there. Now, first step, get it and convert it to moles. So I'm going to go ahead and do that. 1 mole of hydrogen has a molar mass of 2 grams. So that's going to go ahead and give us 15 moles of hydrogen. Next, get my answer, rewrite it. 15 moles of hydrogen. And now I'm going to use the mole ratio. For every 3 moles of hydrogen, you're going to get 1 mole of nitrogen. Now, you might be wondering, why am I looking at the nitrogen, why not the ammonia? Well, my question was figure out how many moles or how many grams of nitrogen. So that's why I'm focusing on the nitrogen, not the ammonia. Alright, so therefore I'm going to put the hydrogen on the denominator. See, they got to match so they can cancel each other out. How many hydrogens? 3 for every 1 mole of nitrogen. So it's going to be 15 times 1 divided by 3. That's going to go ahead and give me 5 moles of nitrogen. Finally, I get my answer from step 2, rewrite in step 3. And what we're going to go ahead and do now is go ahead and convert those moles back to grams. And that's going to go ahead and give us our answer. Alright, so I'm going to put 1 mole on the denominator, and on the numerator is 28 grams. That's the molar mass of nitrogen. Each nitrogen atom is 14. That's the molar mass from the periodic table. And there's 2 of them, so it'll be 2 times 14, that's 28. So in my calculator, we'll put 5 times 28 divided by 1, and our answer is 140 grams of nitrogen. So for every 30 grams of hydrogen, you would need 140 grams of nitrogen to react so that this reaction can take place.